Hi everyone, in this video we are going to discuss about the absolute value function, which is also called the modulus function. The absolute value of a real number is represented between two vertical bars. For example, if we have something like this where you see there is an x between two vertical bars, this represents the absolute value of x. And from the definition of absolute value, the absolute value of a real number is actually the non-negative value of that number. It's actually the magnitude of that number. It's the non-negative value, right? So let's take an example. Suppose we have x equals 5, right? So if we say absolute value of positive 5, that is obviously equal to positive 5. Because absolute value function gives us the non-negative value of the number which is enclosed within the two vertical bars, right? And then if we take absolute value of negative 5, what that will be? Well, because absolute value function gives us a positive value always, it always gives us a non-negative value. So in that case, this is also going to be 5, positive 5 I mean, which can be written as negative of the original number which is between the two vertical bars. The original number is actually negative 5, and because it's a negative number we can write it like this. So positive 5 is actually equal to negative of the negative 5. So from this example, you can clearly see that when the number within the two vertical bars, if that number is not negative, then we get the result as the same number. Like here, if we have a positive number, the absolute value function gives us the same value. But if it is a negative number, then the absolute value gives us something like this. It gives us the negative of that number which is enclosed within the two vertical bars, right? So from the definition then, we can write the definition like this, that the absolute value function can be written as it is going to be same as x or positive x when x is non-negative, and we denote that as greater than or equal to 0. When x is non-negative, then the value of that function is exactly same as x. But it could be negative x when x is actually negative, when x is less than 0. Just look at these two examples here. The first example gives us the first part of the definition, and from the second example we can see the second part of the definition, and we can always express this as a function of x. So here I am writing f of x. Let's assume that this absolute value function is f of x, and then its definition is like this. This is the piecewise form of the function definition. So no matter what we throw inside the two vertical bars, the absolute value function will always convert it into a positive value, and it will give us the positive value. As you can see right here, it always gives us the positive value. Right here you see, this is what we always get. Whether you give him a positive number or negative number, he will always give you a positive value, which is actually called the absolute value or the magnitude of that number. If you remove the sense of direction or the sense of sign, then whatever we are left with, that is nothing but the magnitude of that number, and that's exactly what we get from the absolute value function. So from the definition, we can say that the modulus of a real number or the absolute value of a real number is always greater than or equal to 0. It can never be negative, right? That's by the definition of an absolute value function, that the absolute value operator, the two vertical bars like this, right? This operator always converts any real number into its positive value or into its magnitude, right? So this value which is on the left hand side here, the modulus of x or absolute value of x, I generally call it modulus. It's the term that I am very much used to. So modulus of x is never negative. It's always non-negative. That means it can be 0 or positive. Now when can it be 0? Well, the only time when it can be 0 is when x is equal to 0. If x is equal to 0, then this modulus function can give us the value of 0. So we can say that the equality holds. I'm making a small note here, and if x is any other non-zero number, then the absolute value function will always give us a positive number. And this is an extremely important property that we have to remember, that the modulus of any real number always gives us a non-negative value. So now let's see how the graph of an absolute value function looks like. Suppose we have this function here, so I'm now writing it as y equals f of x, which is the absolute value of x. And we are going to plot the graph of this function, right? So let's try to plot it. To plot the graph, I'm going to make a small little table here, table of the coordinates. So let's try different values of x and see what is the value of y, right? So if we use x as 0, let's try to use x as 0, then y would also be 0 because modulus of 0 would be 0. And if we use x as positive 2, modulus of x would also be positive 2. If we use x as negative 2, then modulus of x would be positive 2 because modulus function always gives us the non-negative value. So y would be 2 because y is nothing but the modulus of x. And similarly, if we take another positive number or negative number, let's take maybe negative 5. If we take negative 5, then also y would be positive 5 because the absolute value of a negative number is again the non-negative magnitude of that number. So now if we plot these points on the Cartesian coordinate plane, it's kind of going to look like this. So here let's try to plot the points. The first point is 0, 0, which is the origin, and I have already plotted that. It's right here. It's at the intersection of the two real number lines there, which are the two axes pretty much. So that is origin 0, 0, and then what would be 2, 2? Well, 2, 2 would be kind of somewhere around here. And then how about negative 2, 2? Well, negative 2, 2 would be kind of around there. And then how about negative 5, 5? Well, negative 5, 5 would be somewhere around here. And then if we are to take maybe one more value of x, say suppose like a positive 5, right? So let's do that. So I'm going to add one more row here. And if the value of x is taken as positive 5, then the value of y would also be 5 because the absolute value of positive 5 would be positive 5. So then this point 5, 5 would be kind of somewhere here, maybe around there. So now let's join these points and see how the graph looks like. So now I'm going to join these points and let me use a different color maybe. So the graph of this absolute value function is going to look like this. There are two straight line segments. One starts from the origin, goes into the first quadrant, and the other one again starts from the origin, goes into the second quadrant. So now if you think about the domain of this function, the domain looks like the entire real x-axis. That means we can give any real value within the absolute value operator and it will give us a valid value for that function. So that means if we give any real number inside the absolute value operator, it will always give us a positive real number. So the domain of this function would be the entire real x-axis. That means all of the real numbers are part of the domain. So now I'm going to make a quick note here. The domain of this function would be the entire real number set. And what about the range? Well, if you think about the range of the function, no matter whether the value of x is positive or negative, the value of y is always positive. That means the range of this function would always be a non-negative value. And how do we indicate a non-negative value? Well, we can use the interval notation to denote it. So the value of y could be 0 or any positive value, right? It's a non-negative value. So we start from 0. So 0 is included. So I'm going to use the interval notation like this, and it could go up to positive infinity. So the range of the function will be like this. Let me highlight it. So the range of the function would be like that, and the domain of the function would be like this. And as you can see, the vertex is actually at the origin. This is what the vertex is. Let me highlight maybe with a red dot right here on the origin. So that is the vertex of this graph. It's a V-shaped graph, and the vertex is actually at the origin. Now we are going to talk about a few important properties of the absolute value function. So let's first talk about this one important property. I'm going to scroll down now. So here goes the first important property of absolute value function. The first property we want to discuss is absolute value of x is equal to absolute value of negative x. Now how do we prove it? Well, it's pretty easy. Let's first look at the left hand side of this equation here. Left hand side, so I'm going to write it as LHS. So here the LHS is, that's the left hand side. Left hand side is actually modulus of x, and can we write it as, it would be positive x when x is non-negative, and it would be negative x when x is negative. So that's the left hand side. And how about the right hand side? Well, let's see what we have on the right hand side. So the right hand side is like this. We have modulus of negative x, and here I'm going to write it like this. I'm going to consider this negative x as a number, right? So I'm just keeping it as negative x. So we are going to say, okay, this is a positive of the number that is within the modulus function. So you just try to look at it from the same definition aspect, that if we assume that whatever is within the modulus sign is a positive value, value, then the piecewise definition of the function will be like this. I'm using the same exact definition. In place of x, I'm now using negative x because that's what we have within the modulus sign, right? And also we have to say negative of the same number when that number is actually negative. I'm going to now write it as negative x. So I'm removing the parenthesis. So I'm simply writing positive of negative x, that is negative x. So the value of this function is negative x when negative x is greater than or equal to 0. And here again I'm removing the parenthesis. So this is becoming positive x because negative of negative x, that is positive x when negative x is less than 0. And from here I'm going to say okay, then that must be equal to. Now if you look at negative of x greater than or equal to 0, so let me do a quick little math there. So if you say negative x is greater than or equal to 0, I'm just looking at this first situation here. So negative x greater than or equal to 0, if we multiply both sides by a negative 1, then what we get? Well, from here if we multiply both sides by a negative 1, then left hand side will become positive x. So let me multiply by negative 1 here. So I'm multiplying negative 1 on the left hand side, and then on the right hand side we have 0 times, again I'm multiplying by a negative 1, and for the inequality sign, the sign will flip because we are multiplying by a negative number on both sides. The inequality sign will flip. So from here we can say that negative 1 times negative x, that is positive x, is less or equal to 0, right? And similarly, if you think about the other piece there, which is when negative x is less than 0, so if negative x is less than 0, then from there can we say, or can we multiply both sides by a negative 1? So I'm multiplying both sides by a negative 1. What will happen to the inequality sign? Well, inequality will flip, so it will become greater than, because you are multiplying both sides by a negative number, the inequality sign should flip. So from here we get that positive x, because negative 1 times negative x, that is positive x, is greater than 0 times negative 1, that is 0. So here you see, if we translate those conditions there, they are now going to look like this, right? So now what we can say, well, then our piecewise function definition is going to look like this: negative x when x is less than or equal to 0, right here, as you can see right here, that's the condition I'm using there. And then it is also equal to positive x when x is greater than 0. And then from here we can clearly say that I'm going to now write the positive x part first. So you can say it will be x when x is greater than 0, and it will be negative x when x is less than or equal to 0. Now guess what? If x is 0, then it is obviously equal to 0. So where you put the equality sign does not really matter when x is equal to 0. So then what I'm going to do, I'm going to now tag the equal sign instead of with the negative of x, I'm going to tag the equal sign right here. I'm going to tag the equal sign right here because the equality always holds when x is 0. So now if you look at the left hand side and the right hand side, now let me highlight this. Do they look identical? Of course they do. So from here we can say, okay, then left hand side is equal to right hand side. So here I'm writing LHS. So our conclusion is that left hand side is equal to right hand side, and we have proved it. Whatever we are supposed to prove, well, we are supposed to prove that modulus of x is equal to modulus of negative x, and we have proved that already. So let's take an example here. Say suppose, so now we know that modulus of x is same as modulus of negative x. Now suppose if we have an example like this, suppose we have modulus of x minus 5, can we write it as modulus of negative of x minus 5? That's exactly what we just proved, and that is now going to look like modulus of, if you now remove the parenthesis, it will become 5 minus x, right? So from here you can see a general picture. The picture is like this, that modulus of x minus a, this is equal to modulus of a minus x. Now we are going to discuss about the next property, which is another important property. So let's talk about that. And the next property says that modulus of x times y is equal to modulus of x times modulus of y. And let's see how we can prove it. Now between two real numbers x and y, if you consider their positive and negative combinations, there could be 4 different scenarios, right? When both x and y are non-negative, and when both of them are negative, and then when one of them is negative and the other one is positive. So I'm going to take multiple cases here. So our case number 1 would be like this. Let's assume that in our first case, both of them are non-negative. So x is greater than or equal to 0 and y is also greater than or equal to 0. That is our first case. And here we are going to say, okay, how is our left hand side going to look like? So our LHS, our left hand side, is actually modulus of x times y, and if both x and y are positive, then how would their product x times y, the product is also going to be positive because both x and y are positive in this particular case. So the product is positive. That means what we have within the modulus sign, that is a positive number, and if it is a positive number, can we say okay, then that must be x times y? It will just come out of the modulus sign exactly as is. Alright, and now how about our right hand side? Well, our right hand side is also going to be like this. So right hand side is now, it is modulus of x times modulus of y. Now because x is a non-negative number, if we remove the modulus sign, it will come out like x times, and also because y is a non-negative number, that will also come out as y. Now in both the cases, you see that our left hand side is looking like x times y and our right hand side is also looking like x times y. So from here, can we say that our left hand side is equal to right hand side? So then for the first case where both x and y are non-negative, we have proved that yes, this property is true or this result is true. Now we are going to take the next case. So suppose our case number 2 is like this. Let's assume that both of them are negative. So let's assume that in this case x is a negative number and y is also a negative number. Then let's see what happens. So in this case, what would be our left hand side? Well, our left hand side is actually modulus of x times y. And if you think about it, when two numbers are negative, their product will be positive. Think about it. If you multiply negative 2 with negative 3, that's going to give you a positive 6. So the product of two negative numbers is also a positive number. So what we have within the modulus sign, that is actually a positive number. And in that case, they will come out exactly like that because that product is a positive number. And now let's look at the right hand side. On the right hand side, we have modulus of x times modulus of y. And because x is a negative number here, so modulus of x will be negative x. It will come out as negative x. That's by the definition. And similarly, because y is a negative number, modulus of y will also come out as negative y. And there again, if you multiply them, they will become positive x times y. So here, as you can see, that the left hand side and the right hand side, they both look equal again. So for the second case also, we have been able to prove that yes, the result is true. The result means the original result that I have highlighted up above, right? Modulus of x times y is equal to modulus of x times modulus of y. Now let's take the third case. So for the third case, let's take x as non-negative and y as negative. Then what would be the left hand side? Well, left hand side has modulus of x times y. Now in this case, if we have a non-negative number and a negative number, their product will be negative. That means x times y in this case is a negative number. And because it is a negative number, it is going to come out with a negative sign and it will come out like this. So now let's take a look at the right hand side. Right hand side has modulus of x times modulus of y. Now if you think about modulus of x, x being a non-negative number, it will come out as positive x. And how about y? Well, y is a negative number, so it will come out as negative y. And now if you multiply both of them, remove the parenthesis, it becomes negative x times y. And here again, if you look at our left hand side and right hand side, I am highlighting them. Left hand side and right hand side, they both look equal. So what does that mean? Well, that means that in the third case also, we have been able to prove that the suggested result, which is modulus of x times y is equal to modulus of x times modulus of y, that is true. Now let's take the fourth case. Well, in the fourth case, let's take x as negative and y as non-negative. Those are the four possible combination of scenarios, right? So this is our final case here. X is negative and y is non-negative. Okay, now what would be the left hand side here? The left hand side is actually modulus of x times y. And if you think about it, here again we have x negative and y non-negative. Their product will definitely be negative. And that means within the modulus sign, whatever we have, the product of x and y, that is actually a negative number. And if it is a negative number, it will come out as a negative sign x times y. Because modulus has the negative value and that negative value will come out of the modulus sign with a negative sign, so that ultimately the value of the modulus is a positive number. number, right? So right here, whatever we have within the parenthesis is actually a negative number, and then it has to be preceded by another negative sign, so that ultimately this entire value right here, let me highlight it, ultimately this has to be a positive number because it is the value of a modulus function, right? Alright, let's now take a look at the right hand side. Well, right hand side has modulus of x times modulus of y, and because x is a negative number here, x will come out with a negative sign, and y is a non-negative number here, so y will come out with a positive sign, and if we multiply them, they becomes negative x times y. And here again, if you look at the value, the left hand side and the right hand side, they are equal. So in all four possible situations, we have been able to prove that the left hand side and the right hand side are equal. That means what we originally suggested here, that modulus of x times y should be equal to modulus of x times modulus of y. That is true. So we have been able to prove that this is true. So now let's talk about the next property, which is very much similar to this. It says that modulus of x over y is equal to modulus of x over modulus of y. So let's see how we can prove it. Well, it's going to be exactly similar as the previous one. So here again, we have to take four different cases when x and y could be both non-negative or both negative or any other combination of negative and positive. So let's take the first case. In the first case, let's take both of them, both x and y, as non-negative. So then, how about our left hand side here? Well, our left hand side has modulus of x over y. And because both x and y are positive, the quotient is also going to be a non-negative value. And because x over y is a non-negative value, it will come out of the modulus sign exactly like that. Alright, now let's take a look at the right hand side. On the right hand side, we have modulus of x over modulus of y, and here x is non-negative, so x will come out as positive x, and y is also non-negative, so y will also come out as positive y. So now you see that both of them, they look exactly identical. That means we can say that the left hand side and the right hand side, they are equal. So you can see that the property is holding true when both x and y are non-negative. Now let's take the second case. So in the second case, we are going to take both of them as negative. So let's say x is also negative and y is also negative. And in this case, let's see what happens. The left hand side will be like this. Left hand side has modulus of x over y. And now think about it. It is the ratio of two negative numbers, or you can say a negative number is divided by another negative number. The quotient will be positive because negative divided by negative is actually a positive number. So x over y is actually a positive number in this case. So it will come out as x over y. I mean positive of x over y. Now let's take a look at the right hand side. There we have modulus of x over modulus of y, and because x is a negative number, it will come out as negative x. Similarly, because y is also a negative number, it will come out as negative y. And from here, what do we get? Well, negative and negative in the numerator and denominator, they're going to neutralize each other. They will become positive y. You can think of it like multiplying both the numerator and the denominator by a negative 1, then it will make it positive, right? So here we are going to get positive x over y. And here again, as you can see, that the value of the left hand side and the value of the right hand side, they both look equal. So from here we can say, well, in this case also, we can clearly see that the left hand side is equal to the right hand side. So that property is still holding true, right? Now let's go for the third case. Here let's take x as non-negative and y as negative, and here again our left hand side is going to look like this. And because we have x as non-negative and y as negative, when x is divided by y, that quotient will be a negative number. The ratio will be a negative number here because one of them is positive and another one is negative. For example, if you say, okay, what about negative, or rather positive 10 over negative 5, we are going to get negative 2 as the quotient. So this division gives us a negative number. So x over y is actually a negative number in this case. So then they will come out of the modulus sign with a negative sign here, right? Now let's see how the right hand side looks like. Well, the right hand side has modulus of x over modulus of y, and here again, because x is non-negative, x will come out exactly like positive x, but because y is a negative number here, it will come out with a negative sign. So in this case also, this can be written as negative of x over y. And here again, we can see that our left hand side and the right hand side, they both look equal. So we can say that LHS is equal to RHS. And what about the next case? Well, let's take the fourth case. Here we are going to take x as a negative number and y as a non-negative number. And left hand side will be modulus of x over y. And now in this case also, you think about it, the division of a positive and a negative number, meaning in this case x is negative and y is non-negative, and of course we have to assume that y is not equal to 0 because we cannot do division by 0, right? So then what would be their quotient? Well, the quotient will again be a negative number because we have dividend as the negative and divisor as the positive. So the quotient will be a negative number, and so if x over y is a negative number, it is going to come out with a negative sign. And then the right hand side is going to look like this. It has modulus of x over modulus of y, and because x is a negative number here, it will come out with a negative sign, and because y is a positive number here, it will come out as just y. So we can again write it as negative of x over y. So here again, if you see our left hand side and the right hand side, they both look identical. That means we can say that the left hand side and the right hand side, they both are equal. So from all four possible situations, we have been able to prove that the left hand side and the right hand side, they are equal. So we can clearly say that this result up here, which says modulus of x over y, will be equal to modulus of x over modulus of y. Well, this video is getting a little longer than I thought. So let's cover the remaining properties of modulus function in the second part of this video. So I'm going to publish this as the first part, and also I'll publish a second part where we'll be discussing about the remaining properties of the modulus function. I hope everything made sense so far. Thank you for watching. See you in the next one.